You need to watch this if you freak out about takeoff. That powerful roar of the engines, the feeling of being pressed back into your seat, it can be a lot. But what if I told you that every sound, every sensation, is part of a perfectly orchestrated symphony of physics? Or if you've ever just looked out the window, thousands of feet in the air, and asked yourself, how does this massive metal tube actually stay up here? It seems to defy logic, doesn't it? A machine weighing hundreds of thousands of pounds, just floating on air. Well, the answer is both simpler and more fascinating than you might think. It's not magic, it's science. And over the next few minutes, we're going to demystify it all. We'll explore the 4 fundamental forces that every single flight contends with. We'll dive deep into the ingenious shape of the wings and see how they work with the air to create the miracle of lift. We'll look at how pilots control these giants of the sky, what happens during each phase of your flight, and even tackle some common myths and fears, like turbulence. By the end, you won't just be a passenger. You'll understand the elegant science that makes modern air travel one of the safest ways to see the world. To understand flight, we first need to meet the 4 main characters in our story: lift, weight, thrust, and drag. These are the 4 fundamental forces of aerodynamics, and they are in a constant tug of war on any object that flies, from a paper airplane to an Airbus A380. First, we have weight. This one's easy. It's the force of gravity pulling the airplane down towards the center of the Earth. Everything has weight, and on the ground, it's what keeps us from floating away. To fly, we obviously need to overcome it. That's where thrust comes in. Thrust is the forward force produced by the engines. Think of it as the muscle. Whether it's a propeller spinning or a jet engine blasting hot gas out the back, thrust pushes the airplane forward through the air. Without thrust, the plane is just a very expensive glider. But as the plane moves forward, it encounters a resisting force called drag. Drag is the friction of the air pushing back against the airplane. You've felt this yourself. Stick your hand out of a moving car window. That force pushing your hand back? That's drag. Airplane designers work tirelessly to make aircraft as sleek and aerodynamic as possible to minimize this force. And finally, the star of the show, lift. Lift is the upward force created by the wings as they move through the air. It's the force that directly opposes weight and holds the airplane in the sky. When lift is greater than weight, the plane climbs. When they are equal, it cruises at a constant altitude. And when lift is less than weight, the plane descends. The secret to how this incredible force is generated lies in the special shape of the wing. So, how do wings create lift? It comes down to a brilliant piece of engineering called an airfoil. That's the technical term for the cross-sectional shape of a wing. If you look at a wing from the side, you'll notice it's not flat. It has a curved upper surface and a relatively flatter bottom surface. This specific shape is the key. As the plane moves forward, the wing slices through the air, splitting the airflow. The air that travels over the curved top has a longer path to travel than the air moving along the flatter bottom. To meet up with the air from the bottom at the back of the wing at roughly the same time, the air on top must move faster. This is where a principle of physics discovered by Daniel Bernoulli comes into play. Bernoulli's principle states that faster-moving air exerts lower pressure. So, because the air is moving faster over the top of the wing, it creates a zone of lower pressure above the wing. Meanwhile, the slower-moving air underneath exerts higher pressure. This pressure difference, high pressure below and low pressure above, creates a net upward force. That force is lift. It's literally pushing the wing and the entire airplane up into the sky. But that's only half the story. The wing also generates lift by applying another famous law of physics, Newton's third law of motion. For every action, there is an equal and opposite reaction. As the wing moves through the air, its shape and slight upward tilt deflect a massive amount of air downwards. Think of it like skipping a stone on water. the stone pushes the water down and the water pushes the stone up. In the same way, the wing pushes air down. The reaction to this downward push is an upward push on the wing. This Newtonian push contributes significantly to the total lift, so it's a combination of both pressure differences and deflecting air that truly makes flight possible. Now the shape of the wing is fixed, but pilots have a crucial tool to control how much lift is being generated: the angle of attack. This is simply the angle between the wing and the oncoming air. By pulling back on the control column, the pilot can tilt the nose of the plane up, increasing the angle of attack. A slightly higher angle deflects more air downwards and can increase the pressure difference, generating more lift. This is how a pilot makes the plane climb without necessarily adding more engine power. However, there's a limit. If the angle of attack becomes too high, the smooth airflow over the top of the wing can detach and become turbulent, like water churning behind a rock in a stream. When this happens, the low-pressure area collapses and the wing suddenly loses most of its lift. This is called a stall. It's important to know that a stall has nothing to do with the engines. It's purely an aerodynamic event. Pilots are extensively trained to recognize and recover from stalls, and modern aircraft have sophisticated warning systems to prevent them from ever happening in normal flight. They always operate with a very wide safety margin. So we know how a plane goes up, but how does it turn, climb, and descend with such precision? This is managed by a set of movable surfaces, primarily on the wings and tail. To bank or roll the aircraft left or right, pilots use ailerons. These are hinged panels on the trailing edge of each wing, way out near the tips. When the pilot turns the yoke, one aileron goes up and the other goes down. The aileron that goes down increases lift on its wing, making it rise, while the one that goes up decreases lift, making its wing drop. This imbalance in lift rolls the plane into a turn. To pitch the nose up or down, pilots use the elevators. These are on the small horizontal wings at the tail. When the pilot pulls back on the control column, the elevators tilt up. This pushes the tail down and, like a seesaw, pivots the nose up, increasing the angle of attack and making the plane climb. Pushing the column forward does the opposite. And for side-to-side control, to nudge the nose left or right, there's the rudder on the vertical tail fin, controlled by the pilot's foot pedals. It works just like the rudder on a boat. Finally, you've probably noticed large sections of the wing moving during takeoff and landing. These are flaps and slats. They extend from the trailing and leading edges of the wing to temporarily increase the wing's curvature and surface area. This allows the wing to generate much more lift at the slower speeds required for takeoff and landing. And those panels that pop up on the wing right after touchdown? Those are spoilers. They spoil the lift and act as air brakes, helping the plane slow down quickly and stay firmly on the runway. Of course, none of this would happen without thrust. The engines provide the essential forward motion that allows the wings to work their magic. Most modern airliners use turbofan engines. You can think of them as a hybrid. At the front is a massive fan that sucks in enormous quantities of air. A small portion of this air goes into the engine's core, where it's compressed, mixed with fuel, and ignited. This creates a high-velocity jet of hot gas that shoots out the back, providing powerful thrust. But the vast majority of the air, up to 90%, simply bypasses the core and is accelerated by the fan, just like a propeller. This bypass air generates most of the engine's thrust and is much quieter and more fuel efficient than a pure jet engine. That deafening roar you hear during takeoff? That's the sound of these incredible machines generating enough power to overcome the immense forces of weight and drag. Every flight follows a predictable sequence. It begins on the ground, taxiing slowly from the gate to the runway. During takeoff, the pilots apply full power, and the plane accelerates rapidly. At a specific speed called V1, they are committed to flying. Shortly after, at rotate speed, the pilot pulls back, the nose lifts, and the plane gracefully leaves the ground. The climb phase is all about gaining altitude efficiently. Once at cruising altitude, usually between 30,000 and 40,000 feet, the engines are throttled back, and the plane settles in for the long haul, with lift perfectly balancing weight and thrust balancing drag. This is the smoothest and most fuel-efficient part of the journey. The descent and approach are carefully managed to arrive at the runway at the correct speed and altitude. Finally, during landing, the pilots use flaps and slats to maintain lift at low speed. And just before touchdown, they perform a flare, raising the nose slightly for a gentle landing on the main wheels first. Ah, turbulence. The one part of flying that makes even seasoned travelers a little uneasy. But what is it? Simply put, turbulence is just irregular air movement. Think of it like bumps in the road or waves on the ocean. It can be caused by weather systems, air moving over mountains, or even the wake from another aircraft. While it might feel dramatic, it's a completely normal part of flying. Airplanes are built to withstand forces far greater than any turbulence they would ever encounter. That wing flex, you see, it's designed to do that. It's a sign of strength and flexibility, not weakness. Pilots and air traffic controllers use sophisticated weather radar to avoid the worst areas. And when turbulence is unavoidable, they simply slow down and turn on the seatbelt sign for everyone's comfort and safety. It's an inconvenience, not a danger. We've talked about the four forces, but engineers are in a constant battle with one in particular: drag. Minimizing drag is the key to efficiency, allowing planes to fly farther with less fuel. There are several types, but a big one is called induced drag, which is created by swirling vortices of air that form at the wingtips. That's why you see those upwardly curved tips on most modern planes. They're called winglets, and they work by breaking up these vortices, reducing drag and saving millions of gallons of fuel across the fleet every year. Engineers also use lightweight composite materials, ultra-smooth paints, and conduct rigorous maintenance to keep every surface as clean and aerodynamic as possible, all in the relentless pursuit of efficiency. Let's clear up a few common myths. Can a cabin door be opened in flight? Absolutely not. The cabin is pressurized, and that pressure seals the door with thousands of pounds of force. It's physically impossible. What if an engine fails? While incredibly rare, planes are designed to fly perfectly safely on one engine. They have more than enough power to climb, cruise, and land normally. And what about autopilot? Autopilot is a sophisticated tool that assists pilots, especially during the long cruise phase, but it doesn't fly the plane by itself. Pilots are always monitoring the systems and are fully in command, especially during the critical phases of takeoff and landing. Flying is, by statistical measure, the safest form of long-distance transportation ever invented, thanks to incredible engineering, rigorous maintenance, and highly trained professionals. So, it all comes back to a few simple, elegant ideas. The shape of the wing creates a pressure difference and pushes air down. The speed from the engines provides the airflow the wings need to work, and the angle of the wing, controlled by the pilot, manages how much lift is generated. Shape, speed, and angle. Together, they equal flight. The next time you fly, as you feel that push of acceleration and see the ground fall away, you'll know exactly what's happening. It's not magic. It's just a beautiful dance with the air. Simple, right?